Every year, humanity extracts over 2 billion tons of iron ore from Earth's crust. Picture this. More than half of our planet's entire weight is iron, most locked in the core, creating the magnetic field protecting all life. But here's what shocks engineers worldwide. We're standing on the most abundant metal in the universe, yet accessing it requires temperatures hotter than volcanic lava. How does rust-colored rock transform into gleaming steel skyscrapers? How do ancient mountains become modern civilization? Stick around till the end. You'll discover why iron shaped human history more than gold ever did, and the jaw-dropping secret hiding inside every bridge, car, and building around you right now. The story begins in Western Australia's Pilbara region, where iron mountains stretch across landscapes older than dinosaurs. Massive excavators, standing 8 stories tall, picture buildings that walk, tear into rust-red cliffs with bucket teeth weighing 12 tons each. These mechanical giants rip through rock layers formed 3 billion years ago when Earth's oceans first rusted. With thunderous crashes echoing across 40-mile-wide craters, each excavator loads haul trucks carrying 400 tons per trip. That's the weight of 80 elephants moving at 40 miles per hour on tires taller than basketball hoops. Processing 30 million tons annually from single mines, enough iron ore to build 12 Golden Gate bridges every single day. Next comes crushing, where house-sized jaw crushers, imagine dinosaur mouths made of hardened steel, pulverize boulders into gravel-sized chunks. With deafening roars splitting eardrums even through protection, these crushers generate forces exceeding 20,000 pounds per square inch. Clouds of red dust billowing upward create artificial sunsets visible from space satellites. Conveyor belts stretching 12 miles long, longer than Manhattan, transport crushed ore at 18 miles per hour. Workers riding inspection carts traverse distances requiring 25 minutes one way. That's enough belt to wrap around 300 football fields. Every hour, 50,000 tons flow through this system, weight equivalent to 5 Eiffel Towers moving continuously past checkpoints. Giant grinding mills, standing 5 stories tall, with diameters matching Olympic swimming pool widths, pulverize rock into fine powder. Inside these rotating drums, 20-ton steel balls, each weighing more than shipping containers, tumble with ore, creating grinding thunder heard miles away. Operators monitor vibrations. Wrong frequencies mean catastrophic bearing failures, costing millions. At rotation speeds creating gravitational forces triple normal Earth gravity, particles shrink to powder finer than talcum. Processing 8,000 tons hourly, that's filling semi-truck after semi-truck every 30 seconds. This powder, called concentrate, contains 65% iron. Magnetic separators then extract iron particles using forces strong enough to levitate railroad spikes, leaving waste rock behind. Next comes the blast furnace, a towering inferno standing 30 stories high, its steel shell glowing dull orange even from outside. At internal temperatures exceeding 3,000 degrees Fahrenheit, hot enough to vaporize aluminum instantly, iron ore transforms into liquid metal. Picture Dante's Inferno engineered with precision. Measured charges of iron ore, coke, and limestone descend from the top, while superheated air blasts upward at 2,000 degrees from ring-shaped nozzles called two airs. This creates a raging chemical storm, where carbon monoxide rips oxygen from iron oxide molecules. The reaction releases enough heat to melt granite. Every 3 minutes, sensors check 20 different parameters. Without precision, furnaces explode with force demolishing city blocks. The blast furnace operates continuously for 15 years, never cooling, never stopping, like Earth's core relocated to industrial facilities. Inside this chemical reactor, materials descend through distinct zones. Upper regions preheat incoming ore. Middle zones drive off moisture and carbon dioxide. Lower depths become hell itself, where iron liquefies. At the hearth bottom, molten iron collects at 2,800 degrees Fahrenheit, dense as lead but flowing like water. Every 4 hours, workers drill through clay-plugged tap holes. Liquid iron erupts in blinding white rivers, flowing through ceramic channels into railroad cars holding 300 tons each. This step is critical because timing determines metal purity. Tap too early, slag contaminates. Too late, furnace pressure ruptures containment walls. After tapping, slag, lighter impurities floating atop molten iron, gets diverted into separate channels. This glowing amber liquid, essentially liquefied rock, contains calcium, silicon, and aluminum oxides stripped from ore. Rather than waste, it becomes roadbed material and cement ingredient, recycled at 98% rates globally. The molten iron, called pig iron, contains 4% carbon, too brittle for construction. Picture glass that looks metallic. Drop pig iron from waist height, it shatters into fragments. Next comes the basic oxygen furnace, where pure oxygen blasted at supersonic speeds through 3-foot diameter lances burns away excess carbon in 17 minutes. Flames shooting 70 feet high, temperatures hitting 3,200 degrees, create hurricane-force winds inside steel vessels holding 350 tons of liquid metal. Steelmaking requires precision rivaling brain surgery. Computer-controlled oxygen flow adjusts by milliseconds. Operators add exact amounts of manganese, silicon, chromium, elements changing steel properties dramatically. Too much carbon, steel cracks in winter cold. Too little, metal bends under load. Picture this: alloying elements get injected via submerged lances. Electromagnetic stirring, invisible but powerful, homogenizes composition. Samples extracted every 3 minutes get analyzed via spectrometers, determining chemistry within seconds. Modern furnaces achieve carbon content accuracy to 0.01%, difference between skyscraper standing or collapsing. After refining, liquid steel flows into continuous casting machines producing slabs 30 feet long, weighing 25 tons at rates of 1 slab every 90 seconds. This wasn't always so advanced. Back in ancient Anatolia around 1300 BC, Hittite metallurgists discovered heating iron ore with charcoal produced workable metal. That breakthrough, accidental furnace conditions reaching iron's melting point, changed human civilization forever. Iron tools outperformed bronze, enabling agriculture revolution. The breakthrough came when British inventor Henry Bessemer patented his converter in 1856, slashing steel production time from 24 hours to 17 minutes. Suddenly, steel costs dropped 90%. This single invention built modern cities. Skyscrapers, bridges, railroads exploded across continents. Today, global steel production exceeds 1.9 billion tons annually. That's enough to build 75,000 Eiffel Towers yearly, or manufacture 43 million automobiles, or construct bridges connecting every coastline on Earth. Carbon emissions drop by 62% when using recycled steel versus virgin ore, equivalent to removing 12 million cars annually. Industry saves over $80 billion yearly through scrap recycling. Processing costs drop 43% because melting scrap requires 1/3 the energy of blast furnaces. So here's the secret promised: every ton of steel you see, bridges, buildings, cars, will be recycled indefinitely. Unlike plastic decomposing into microparticles or paper pulping into mush, steel never degrades. Magnetic separation extracts it perfectly from demolished structures. That girder in your office building might contain steel from 1930s locomotives. Your car's frame could include battleship armor from World War II. Nothing disappears. Metal merely transforms, reborn eternally. From ancient mountains to modern marvels, cycle completes. Iron, humanity's most essential metal, circulates through civilization like blood through veins. We're not consuming Earth's iron, we're borrowing it, briefly, before passing it forward to futures we'll never see.
The largest gasoline production plant in the United States is Marathon Petroleum's facility in Galveston Bay, Texas. It's a true giant, processing 631,000 barrels of crude oil every day. That's about 26.5 million gallons every single day, a staggering number. Let's dive into the atmosphere of oil refining production. It all began long before the era of hybrids, electric cars, and climate summits. Back in the days when America was still smoking and roaring, the world needed fuel, and Texas provided it by the spoonful. On the coast of the Gulf of Mexico, in the Texas city of Texas City, a decision was made back in 1931 to build a plant that would refine oil into liquids that make cars and airplanes roar. By 1933, the plant was operational. At that time, it belonged to Republic Oil, and a little later, it was taken over by Amoco, which eventually became part of British Petroleum. Those were wild times. Every day, a new record. Gallons of gasoline flowed like a river, and the plant gradually expanded. It survived World War II, the oil crises of the 70s, and even an explosion in 2005 when 15 workers died at a neighboring facility. A tragedy that forced a complete overhaul of safety in the entire oil refining region. Have you heard about it? And so, in 2013, the giant changes hands. Marathon Petroleum Corporation buys the plant. And they don't just buy it, they integrate it with their own refinery located nearby. Thus, a single gigantic system is born, the Galveston Bay Refinery, which since then has been processing over 630,000 barrels of crude oil every day. To imagine the scale, that's over 26 million gallons of fuel per day, and the complex covers nearly 1,000 acres. Over 1,500 people work there, not counting contractors and specialists who service the units. It's like a small industrial city, only instead of coffee shops, there are reactors instead of fountains, cooling towers, and instead of a park, thousands of pipelines. Galveston Bay is the pulse of the US fuel infrastructure. It operates 24 hours a day, 7 days a week, without stops or breaks. It's not just gasoline that's born here, they also produce jet fuel, diesel, fuel oil, petroleum coke, and even propylene for the chemical industry. Everything that can flow, burn, and work is squeezed out of every drop of crude oil. Interestingly, the plant's location is strategic. The nearby port allows for receiving tankers from all over the world and a network of pipelines and railways for sending products all over America. Roughly speaking, if you're filling up your tank somewhere in the US, there's a chance that at least a drop of that fuel passed through the furnaces of Galveston Bay. And although the world is changing today, and green energy is being talked about from every microphone, the Galveston Bay Refinery is not giving up its position. Marathon Petroleum is investing hundreds of millions of dollars in modernization, filtration, and reducing harmful emissions. Because as long as the planet is still roaring with engines, this Texas giant remains at the heart of the American highway. We are heading to a territory where it doesn't smell of flowers, but where pipes roar, signal lights flash, and black gold is turned into gasoline. Galveston Bay Refinery, one of the largest plants in the US, and production there begins not with the push of a start button, but with thousands of miles of logistics, pressure, and thermal alchemy. The first drop of oil in this story doesn't yet have the smell of gasoline. It's in its raw form, viscous, dark, with impurities, water, sulfur, and metals. It's delivered by tankers through the port of Texas City, or pumped through pipelines that stretch for thousands of kilometers. This plant can receive over 1 million barrels of crude oil per week. That's an insane amount. The oil goes into huge tanks, so-called crude tanks. Each such tank can hold 500,000 barrels. Imagine that, that's more than 20 million gallons. Here it is stored for several days, where it settles and is heated to a temperature of about 140 degrees Fahrenheit to reduce viscosity and facilitate pumping. Next, the oil goes through desalters. These are special units that remove water, salts, and mechanical impurities. Because salts are death to metal reactors, they cause corrosion and form dangerous deposits. Here, the oil is mixed with fresh water and electrical energy, creating an emulsion that forces the impurities to separate. This is, essentially, industrial cleaning. After this, the main stage, the atmospheric distillation unit. A tower 230 feet high, where oil heated to 650 degrees Fahrenheit is fed in, and vapors rise to the top. And here the magic begins. Heavy fractions like diesel, kerosene, and fuel oil settle at the bottom, while lighter ones, the gasoline fraction, naphtha for petrochemicals, rise to the top. You can imagine this tower as an oil elevator, where each floor is a separate product. The temperature in the column plays a key role. At each height, its own condensation point. Heavy components stop faster, light ones fly further. All this works in real time with control over every degree and every drop. But no, this isn't gasoline yet. What has been collected are raw fractions that are then sent to other units. Vacuum distillation, catalytic cracking, hydrotreating, and only then to blending. That is, mixing to meet the standards for gasoline, diesel, and jet fuel. By the way, gasoline itself is not a single component, but a mixture of dozens of fractions that are chemically and physically stitched together into a precisely calibrated formula, with an octane number, ignition temperature, volatility, aromatics, all according to standard. But let's go back. After the atmospheric tower, many heavy fractions are sent to a vacuum column, where they are distilled under reduced pressure, so as not to burn them to a crisp. From there come components for lubricants, bitumen, and even raw material for plastics. Then even deeper, catalytic cracking, where molecules are literally broken into smaller ones, turning heavy fuel oil into light gasoline. And only when this black magic is complete does the collection of fractions, mixing, adding additives begin, and at the end, storage tanks with the finished product, which again await tankers, pipelines, and rail cars. After all the formidable reactors, furnaces, and towers, where crude oil has been given a good heating, the crucial stage arrives: final blending. This is no longer a turbulent boiling or flowing in pipes. It's like a chemical kitchen, where a complex dish with a taste of power and precision is prepared from a few simple ingredients. Each fraction obtained from previous processes has its own properties. One is light, volatile, with a low octane number. Another is heavier, dense, resistant to temperatures and pressure. From these, like from puzzle pieces, petrochemical technologists assemble the required mixture. This is called blending, and this is the moment when gasoline essentially is born. It is not mixed randomly. Everything happens according to precisely calculated formulas. The fractions are fed into mixing tanks, where every drop is controlled by automation. Machines know exactly how much of what to supply to get the desired grade of gasoline at the output, with a certain octane number, resistance to detonation, and stability during storage. But even the most precise mixing is not the end. Special additives are added to the gasoline composition. These are small in volume, but powerful in effect substances. It is they that help the fuel work better, not destroy engines, not rust in tanks, not evaporate too quickly, not clog injectors, not pollute the atmosphere. Additives are introduced in microscopic doses, literally a few ounces per gallon, but modern fuel is impossible without them. When everything is ready, the gasoline goes into finishing tanks. These are giant steel containers located next to railway lines, truck ramps, and port pipelines. There, the fuel can be stored for days or weeks, waiting for its time. Then, shipment, tankers, rail cars, barges. And so, the fuel hits the road. Maybe this very batch of gasoline will be hissing in the tank of your car in a few days. Maybe it will power a combine, a truck, a boat, or an airplane. But whatever the case, this gasoline has come a long way. From dark, raw mud to perfect, transparent fuel. It is clean, stable, ready to burn, but only when you say, "Start your engine." Every year, over 3,000 tons of gold are mined worldwide. But you'll be surprised, a significant portion of this shiny treasure doesn't stay in mines or banks, but heads to a place where gold literally turns into art: Dubai. In a city that trades over $129 billion in gold annually, ingots become masterpieces that shine in the 300 shops of the legendary gold souk. What is really hidden behind the glitter of jewelry? ancient rituals, or cutting-edge technology? If you watch until the end, you'll discover a golden secret that almost no one knows. Our journey begins not in a luxury boutique, but in the bustling cargo terminal of Dubai's airport. It is here that tons of gold arrive from over 100 countries around the world, from distant mines in Africa, Australia, and America. These planes are not carrying passengers, but a precious cargo in the form of large, heavy ingots. Part of them is so-called doré gold, unrefined, with impurities of other metals, straight from the mines. Another part consists of standard bank ingots, but they all have a long path of transformation ahead of them. Dubai is not a mining location. It's a giant, incredibly powerful melting pot and production center, the largest gold hub on the planet. The first stop for our gold is a refinery. This is a true high-tech fortress, better protected than a bank. Here, the sacred act of purification takes place. Ingots are loaded into giant induction furnaces. The air is filled with a hum and heat. The temperature inside exceeds 1,900 degrees Fahrenheit, and the solid metal turns into a liquid, dazzlingly bright sun. The liquid gold boils, and impurities float to the surface, which are carefully skimmed off. But this is not enough to achieve perfect purity. Next, chemistry comes into play. The gold goes through complex electrolysis processes, such as the Miller and Wohlwill processes, where an electric current and chemical reactions are used to remove absolutely all foreign metals. The goal is to achieve a purity of 999.9, so-called 4 nines, the highest standard in the world. At the output, we get ingots of pure, almost otherworldly gold, shining with a deep, rich yellow color. But surprisingly, jewelry is rarely made from such pure 24-karat gold. Why? Because it's too soft. A ring made of pure gold could be deformed by a simple handshake. And this is where true jewelry science begins. To make gold strong and give it different shades, it is alloyed with other metals. This process is called alloying. Pure gold is melted again, and a strictly measured amount of ligature, an alloy of copper, silver, palladium, or zinc, is added to it. Do you want the classic yellow gold, so beloved in the East? Add a little silver and copper. Dreaming of romantic rose gold? Increase the share of copper. And for elegant white gold, palladium or nickel is needed. This is how different purities, or carats, are born. In the Dubai market, the most popular are 22 carats. This is 91.6% pure gold and 18 carats. That's 75% pure gold, which are the perfect compromise between purity and practicality. Now that we have a gold alloy of the desired color and strength, the most interesting part begins, the creation of the jewelry itself. And here, Dubai demonstrates all its versatility, combining futuristic technologies with a craft that is thousands of years old. Many pieces begin their life on a computer screen. Jewelry designers create complex three-dimensional models using CAD software. They can draw every detail, every swirl of a future necklace or earrings. Then this digital model is sent to a 3D printer, which, not from plastic, but from a special wax, grows a precise copy of the jewelry layer by layer. It's a wax wonder. Next, this wax model, or wax pattern, becomes the basis for casting. It is dipped into a special plaster-like mixture that hardens, forming a mold. Then this mold is heated. The wax melts out, leaving behind a perfectly accurate hollow impression of the future jewelry. And here it is, the moment of truth. Molten, red-hot gold is poured into this mold under pressure, or with the help of a vacuum. Every minute detail, reproduced with computer accuracy, is filled. When the metal solidifies, the plaster mold is broken, and a rough gold piece is born. But this is just a skeleton. Now master jewelers, whose skills have been passed down from generation to generation, get to work. They grind, polish, assemble individual parts, turning metal into a work of art. Imagine these workshops filled with the buzzing of drills, the quiet tapping of hammers, and the focused faces of the masters. They use techniques that haven't changed for centuries, creating the finest patterns from wire, inlaying pieces with precious stones, engraving complex Arabic ornaments. This is painstaking manual labor that requires incredible skill and patience. Each stone is set by hand, each link of a chain is checked for strength, and, of course, quality control. The government of Dubai is extremely strict about the reputation of its main market. Every piece undergoes a mandatory check in the municipal laboratory. A special hallmark is stamped on it, confirming the carat. This is a guarantee of authenticity. You will never buy a fake in an official Dubai store. This strict control system has created the city's reputation as the most reliable place to buy gold in the world. And so, having gone through this long and complex path, a piece of gold jewelry ends up in the window of one of the more than 380 shops of the legendary gold souk in the Dera district. This is a place where history meets luxury. A market that started in the 1940s as a small group of merchants from India and Iran has turned into a global center of attraction for everyone who appreciates the beauty of gold. Here you can see everything, from modest chains to giant wedding necklaces weighing several pounds, from classic Arabic designs to ultra-modern European styles. The air here is thick with the excitement of bargaining and the enthusiastic exclamations of tourists. This is not just a market, it's a show, an attraction, an open-air museum. This is the journey of gold in Dubai. From a formless piece of metal, mined thousands of miles away, through the fire of furnaces and the hands of talented masters, to a dazzling masterpiece waiting for its owner in the world's capital of glitter. It's a process where modern technologies serve ancient art and strict control guarantees quality. And all this to maintain the loud and absolutely deserved title, City of Gold. Incredible, isn't it? Dubai has firmly established itself as one of the leading global gold trading centers, ranking second in the world in 2023 by trade volume, surpassing the United Kingdom. The total value of gold trade in the UAE that year exceeded 129 billion US dollars, which is 36% more than in the previous year. This highlights the rapid growth and strategic importance of the emirate in the global precious metals industry. Between 20 and 30% of the entire world's gold circulation passes through Dubai annually. Gold trade accounts for almost 30% of the UAE's total non-oil exports, which indicates a successful diversification of the economy. Last year, over 5,400,000 contracts were concluded on the Dubai Gold and Commodities Exchange for a total amount of over $1 billion, $115 billion. Gold and silver futures amounted to 80,000 contracts for a total of over $44 million. The dynamics of the gold market in Dubai are influenced by global economic uncertainty, fluctuations in the US dollar exchange rate, to which the UAE dirham is pegged, and stable demand from investors and consumers. In times of instability, gold is traditionally seen as a safe haven asset for investment. Analysts predict further market growth. The gold bullion market in the UAE is expected to grow at an average annual growth rate of almost 10% until 2031. This will be facilitated by a business-friendly regulatory environment, a developed logistics infrastructure, and the absence of value-added tax on gold. The UAE's entry into BRICS Plus in 2024 opens up new opportunities for expanding gold trade with other market giants. Every year, over 4 million tons of steel wire rope are produced worldwide, and it's these thin, shining threads that hold up bridges, elevators, lifts, and ships. But what if I told you that before becoming a rope, every wire goes through real torture acid, flame, a press, and a tension capable of tearing steel apart? In this video, we'll show you how a piece of rough wire rod is born into a perfectly smooth metal thread, capable of withstanding thousands of tons of load. And at the end, you'll learn something that even the manufacturers themselves keep hidden. To create a steel cable capable of holding up a bridge hundreds of feet long, it all starts with the right alloy. Most often, it's carbon steel with a carbon content of around 0.6%, which provides both strength and elasticity. Sometimes chromium, nickel, or molybdenum are added for corrosion resistance and increased load capacity, especially for cables that need to work outdoors for decades. The metal is delivered to the factory in the form of huge steel slabs plates measuring 10 by 2 by half a foot and weighing up to 10 tons. They are heated in furnaces to 2,200 degrees Fahrenheit until the steel becomes plastic, almost like rubber. Then these red-hot billets are passed through rolling mills, turning them into long, thin rods with a diameter of approximately 0.25 inches. These are called wire rods. These wire rods are then cooled under controlled conditions, either in air or in special baths, so that the metal structure is dense and the internal stress is uniform. Next, a short storage stage. The metal is weighed, checked for hardness, flexibility, and the presence of microcracks. Only after this is each coil sent to the main section wire drawing, from which the future cables will be formed. After the steel wire rods have been cooled and checked for quality, they proceed to the wire drawing workshop. This process transforms the thick rods into thin but incredibly strong wire, which will become the foundation for bridge cables. Imagine a steel rod as thick as your finger, just off the billet. Its surface is rough, as if covered in a layer of sand or rust. This is scalar hard and brittle crust that appears during hot rolling. To prevent it from interfering with further metal processing, it needs to be removed. To do this, the wire rod is first lowered into a bath of acid solution, usually sulfuric or hydrochloric acid. In this solution, the scale seems to flake off the metal, just like old paint peels off after being treated with solvent. Then the wire is rinsed with a large amount of water under pressure to wash away all traces of acid and dirt. To the touch after this, the metal becomes smooth and cool, like a freshly polished stone. But that's not enough. Next, the wire goes through degreasing. It's submerged in special alkaline solutions that remove any oils that might have gotten onto the surface. And only then is the clean, smooth wire, shiny and dry, ready for the next stage drawing. Now the wire needs to be pulled through a hole smaller than the wire itself to stretch it out and make it thinner. But a thick end simply won't fit through. So, it's first sharpened. This process is called pointing. The wire is fixed in a special mechanism that resembles strong metal vice jaws. One end of it is inserted into a device similar to a small press or crusher, where the steel casing is gradually squeezed and stretched into a cone shape. This way, the wire is essentially machined into a pointed tip. Imagine a pencil sharpened at one end, only it's not graphite but cold, shiny metal. This sharpened end then easily fits into the first opening of the drawing machine, a small metal die. To the touch, such a sharpened part becomes thin, like a shoelace, but remains elastic and strong. This is where the drawing process begins, which will turn the rough wire rod into a thin steel wire for the cable. Picture a shining metal strand, about the thickness of a pencil, being gradually pulled through a series of metal rings. Each of these rings is a drawing die, looking like a coin with a hole in the middle, but made of super hard material, like tungsten carbide. The holes in each die are slightly smaller than the previous ones. The whole system is arranged in a line, like beads on a thread. The wire passes through the first ring, and it compresses it, stretches it, reducing its diameter. Next, the following ring, even smaller, and the same thing happens again. The entire wire is pulled by a powerful drawing machine, resembling giant toothed rollers or high traction rollers. It constantly pulls the wire forward, maintaining tension, and thus forcing it to pass through the dies. To the touch, after several passes, the wire becomes thinner and longer, like a silvery strand of hair. The surface is smooth, cool, with a clear metallic sheen. Importantly, this entire process happens without heating. The metal remains cold. That's why it's called cold drawing. The steel gets stronger in the process. Its structure becomes denser and more durable, like a muscle that's been trained. And so, ring after ring, an ordinary wire rod transforms into a high-precision wire for a future steel cable. The steel thread that has just passed through a series of drawing dies has become thinner and stronger, but at the same time stressed, like a stretched string with fatigue hidden inside. The metal has accumulated internal stresses, microscopic defects that reduce its ability to bend or stretch further without cracking. Yes, this wire has become brittle. To release this stress, the wire passes through a special thermal furnace. It's not visible from the outside. It's a long metal tunnel structure, inside which the temperature reaches over 1000 degrees Fahrenheit. In such heat, resembling the middle of a bonfire, the wire slowly moves through the furnace, either lying on moving rollers or suspended. It gradually heats up to the required temperature and then slowly cools down. The whole process takes anywhere from a few minutes to an hour, depending on the thickness and grade of the steel. To the touch, the wire after this stage is just as smooth and shiny, but it no longer breaks. Inside the metal, its crystalline structure has rearranged itself. The stresses are relieved, plasticity is restored. Now it's ready for the next series of drawings, and it will become even thinner, stronger, and more durable. It's like giving your muscles time to recover before the next workout. In the final stage, the wire undergoes a final quality control, and this is definitely not a simple visual check. A long, almost continuous strand of shiny metal moves at a speed of tens of feet per second through the inspection unit. There, it's met by special sensors. This could be laser equipment that non-contact measures the wire's diameter with an accuracy of thousandths of an inch. Nearby devices that determine strength. A portion of the batch is selected for mechanical testing. The wire is clamped in hydraulic jaws and pulled until it breaks. This determines its tensile strength and breaking load. If the wire holds up, it's ready for work at heights of hundreds of feet, supporting the weight of a car bridge. The surface is checked separately for micro cracks, burrs, corrosion. High-resolution cameras or even eddy current testing are used here, which can see beneath the top layer of metal. And only the wire that has passed all these tests gets the green light. It will become part of a steel cable capable of withstanding years of loads and harsh weather. This is the final touch that guarantees what arrives at the construction site is reliable, like steel itself. After inspection, the quality wire is neatly wound onto large spools. The wire passes through guide rollers and tensioning mechanisms that ensure the coils lie tightly, but not too tightly. All this happens on high-speed winding machines. Spools come in different sizes. For thin wire, they might weigh hundreds of pounds. For thicker wire, a ton or more. Then these spools head to the next stage, the actual twisting into cables. But even before this, they are sometimes coated with an anti-corrosive compound or lubricant so the wire isn't damaged during storage and transport. Spools of wire are usually moved using forklifts, cranes, or special carts because the weight of even one spool can reach several hundred pounds or more. Manual labor is out of the question here. Otherwise, the risk of injury would be too high. Every year, thousands of tons of fiberglass rebar are produced worldwide. a material that's throwing down the gauntlet to steel. Imagine hundreds of spools of fiberglass, thinner than a human hair, merging into a single river, passing through sticky resin baths, red-hot dyes, and scorching ovens to be born as a rod that's 4 times lighter than steel, twice as strong, and completely immune to rust. This rebar is capable of doubling the lifespan of concrete structures and changing cities forever. But the most interesting part is hidden in the very heart of this process. If you watch until the end, you'll discover a secret that will completely change your understanding of the future of construction. It all begins at one end of a massive workshop, where a structure resembling a giant library for threads stands. This is called a creel. On a wall several yards high, hundreds, and sometimes even thousands, of huge bobbins are installed in neat rows. On each of them is wound the finest glass thread, or roving. This isn't the kind of glass that windows are made of. This is a special fiberglass, produced by melting glass and drawing it through microscopic holes. The result is threads thinner than a human hair, but with incredible tensile strength. These will be our skeleton, our internal army that will give the rod its insane strength. From each of these hundreds of spools, its own separate thread is drawn, and they all come together into one thick, fluffy strand. It's like thousands of small streams merging into one large river. This dry, white strand is the soul of the future rebar. Next, this river of fiberglass begins its journey. It passes through a system of guides and tensioning devices. This is a very important, though inconspicuous, stage. Every one of the thousands of threads must be tensioned with the same force. If one thread sags, while another is too tight, the load in the final product will be distributed unevenly, and it will lose its strength. Therefore, the machine carefully aligns them, preparing them for the most important moment: a baptism in resin. The dry glass strand is slowly submerged into a bath filled with a thick, sticky liquid, similar to honey or syrup. This is a polymer resin, our meat that will grow on the glass skeleton. It's a complex chemical cocktail. The base is usually a polyester, vinyl ester, or epoxy resin. A hardener is added to it, a catalyst that will trigger a chemical reaction and force the liquid to turn into a solid plastic. Various additives can also be added here. Pigments to add color, ultraviolet inhibitors so the rebar isn't afraid of sunlight, and flame retardants for fire resistance. The task of this bath is to saturate every single, even the tiniest fiber. The strand must be completely submerged in this resin so that no dry spots remain. The saturated strand, heavy with sticky resin, exits the bath and heads to its point of birth, the forming die. This is the heart of the whole process. Imagine a thick steel plate with a perfectly round polished hole, the diameter of which exactly matches the diameter of the future rod. The die is heated to a certain temperature. When the wet strand is pulled into this hole, several things happen at once. First, the die, like a press, squeezes out all the excess resin, leaving only the necessary amount. Second, it tightly compresses all the fiberglass strands together, forming a perfectly round rod. Third, the heat from the die initiates the initial stage of the chemical hardening reaction, or polymerization. The resin begins to transform from a liquid into a gel. At the exit of the die, we can already see the familiar shape of the rod, but it is still soft and vulnerable. But how does it get its famous ribbed surface to hold well in concrete? Immediately after exiting the die, while the rod is still hot and soft, a special strand of the same fiberglass is wound around it. A thin, resin-saturated thread is wound in a spiral on the surface of the rod, creating a relief pattern. Sometimes, for even better adhesion, fine quartz sand is sprinkled onto the sticky surface, which adheres permanently to the resin. Now, our rebar has not only strength, but also teeth with which it will hold onto the concrete. The formed and wrapped rod enters the longest part of the machine, the curing tunnel, or polymerization oven. This is a long chamber that can extend for tens of feet, inside which a high temperature is maintained, usually 400 degrees Fahrenheit. Here, the final transformation takes place. This is not just drying. Under the influence of heat, the resin molecules begin to actively bond with each other, forming a strong, rigid three-dimensional network. The liquid, sticky syrup turns into an extremely strong and hard composite material that permanently binds millions of glass fibers into a single monolith. It's like baking a pie. As the rod slowly moves through this hot tunnel, it acquires its final, rock-solid hardness. But what pulls it through this entire long journey, from the spools to the oven? At the end of the line stands a special pulling device, which gives the whole process its name. Usually, it's two caterpillar-like mechanisms, similar to tank tracks, located one above the other. They gently but very firmly clamp the already finished hard rod with their rubber pads and pull it towards themselves at a constant, precisely calibrated speed. It is they that create the force that pulls the fiberglass through the resin bath, through the forming die, and through the oven. The speed of this movement is one of the most important parameters that controls the quality of the final product. And so, from the other end of this long conveyor, an endless, perfectly straight, hard and hot fiberglass rod emerges. The final cord is cutting. An automatic saw is installed across the line. It synchronizes with the speed of the rod's movement, at the right moment makes a quick forward motion, and with a sharp zzzt, cuts a piece of standard length, for example 20 or 40 feet, from the endless ribbon. Then it returns to its starting position, waiting for the next section to arrive. The finished, still warm rods roll onto a cooling table, and then they are collected into bundles, tied, and sent to the warehouse. And just like that, before our eyes, thousands of fragile glass threads and a barrel of sticky liquid, having passed through baths, presses, and ovens, have turned into a lightweight but incredibly strong building material of the future, ready to challenge rust and time in the concrete jungle. The fiberglass rebar market is not yet a giant like the steel market, but it's the coolest and most audacious newcomer at the party, rapidly gaining popularity. The global market for this material is already valued at hundreds of millions of dollars, and the forecasts are just insane. It's expected to grow by 10 or 12% annually. This means that more and more engineers and architects are looking at rusting steel and saying, "Dude, we can do better." And now for the main features that make steel rebar nervously smoke in the corner. The first and most obvious is weight. Fiberglass rebar is about 4 times lighter than steel of the same diameter. Sound boring? Now imagine this in real life. Imagine a truck carrying rebar to a construction site. It can bring 4 times more length of fiberglass rebar in one trip than steel, because it's limited by weight. Or for the same amount, it will take 4 times fewer trips, which saves fuel and time. On the site itself, 2 workers can easily carry whole coils or bundles of fiberglass rods, whereas moving steel requires a crane. This is a colossal saving in logistics and labor. Second is strength. And here, fiberglass just steps into the ring and knocks out steel in the first round. Its tensile strength is about twice as high as that of standard steel rebar. So you understand, to break a fiberglass rod, you need to apply twice as much effort as for a steel one of the same diameter. This means that in some structures, rebar of a smaller diameter can be used, saving even more weight and volume. It's like comparing a regular rope with a climbing rope. At a smaller thickness, it can withstand much greater loads. But the main trump card, the real superpower of fiberglass, is its war against rust. The main enemy of any reinforced concrete structure, from bridges to parking garages, is not the load. It's rust. Water and salts penetrate through micro cracks in the concrete, reach the steel rebar, and it begins to rust. The rust expands in volume and literally tears the concrete apart from the inside. Annually, the US spends billions of dollars on repairing bridges, parking garages, embankments, and tunnels destroyed by rebar corrosion. And fiberglass? It just laughs in the face of rust. It is chemically inert. It is completely indifferent to water, salt, acids, and alkalis. This means that the service life of the structure increases dramatically. A concrete structure reinforced with steel is designed for more than 50 years, and a structure with fiberglass rebar is easily designed for more than 100 years. Every year, Over 4 billion miles of fiber optic cables are produced worldwide. That's enough to wrap around the Earth more than 160 times. But few people know that their journey begins with sand. A special kind, whose purity is measured in parts per million. Because even one microcrack can destroy a signal that's racing for thousands of miles at the speed of light. What is this magic? How does ordinary sand turn into transparent threads, thinner than a hair, but stronger than steel? Watch closely. At the end of this video, you'll learn a secret you've never heard before. To create a thread capable of transmitting light at a speed of over 186,000 miles per second, you have to start with sand. But not just any sand, only special, extremely pure quartz sand, where the main substance is silicon dioxide. For fiber optic production, sand with a silica content of over 99.9% is used, which means in 1 million parts, there's only 1 part of impurities. Imagine this. In every pound of raw material, no more than a few millionths of an ounce of impurities. And this is critical, because even 1 billionth of an inch of foreign metal or organic matter can cause light scattering or absorption in the fiber optic cable. And then the signal, which was supposed to travel 60 miles without amplification, simply disappears. Raw material for fiber optic cable isn't just washed or filtered, it's purified at the molecular level. Manufacturers often use vapor phase chemistry. Quartz sand is converted into gaseous silicon tetrachloride, which is then distilled, filtered, and deposited as pure vapor. And only then is it converted back into glass. Add to this strict control of temperature, humidity, and air currents in clean rooms, and you'll get an idea of how far this is from an ordinary sandy beach. Production laboratories look more like National Aeronautics and Space Administration sterile zones than a glass workshop, and all for the sake of ensuring there's not a single defect in every yard of the future fiber. Because when you're transmitting light over thousands of miles, even one microscratch can cost you signal quality. A large, transparent glass cylinder that will later be melted and drawn into a very thin thread. This is the fiber optic preform. This huge glass rod is made using a method called vapor deposition. In a large furnace, air is mixed with very pure gases. These are different substances that turn into vapor when heated. These vapors hit the inner surface of a transparent tube, which is heated very intensely. When the vapors touch the hot wall of the tube, they deposit and turn into tiny droplets of glass, like dew collecting on leaves in the morning. Gradually, these droplets collect, layer by layer, until a thick layer of glass forms inside the tube. Then this tube is heated even more intensely, and it collapses into a dense solid rod, and this is our preform. The preform is placed in a special furnace that heats up very intensely. The temperature inside it reaches approximately 4,700 degrees Fahrenheit. This temperature is so high that the glass becomes soft and starts to melt, like caramel on a stove. When the end of the preform melts, a drop of molten glass begins to drip from it. This drop is very carefully drawn downwards, and a thin thread is formed from it. This thread, the optical fiber, is drawn at a speed of approximately 1,000 feet per minute. Imagine that. It's faster than a cyclist moving through the city. It's important for the thread to be of uniform thickness throughout its length. The thickness of an optical fiber is usually around 125 microns, or approximately 0.005 inches. That's very, very thin. For comparison, the average human hair is about 100 microns thick or less. To keep this diameter under control, special instruments are used during the process. They look at the thread in real time and measure its thickness. If the thread starts to become thicker or thinner, the system automatically changes the drawing speed or the furnace temperature to correct it. After the optical fiber has been drawn from the preform and has become a thin, transparent thread, it needs to be protected. The fiber is very thin and fragile. If left unprotected, it can easily break, cracks will appear, or dirt will get on it. Therefore, immediately after drawing, the fiber is coated with a special protective layer. A thin thread is pulled from the furnace. After the furnace, the thread immediately goes into a coating machine. This is a special device that clothes the thread in a plastic sheath. The optical fiber enters a special part of the machine called the coating head. It's like a small tube, or nozzle, inside which there's molten protective material. As the fiber passes through this tube, a layer of liquid polymer is evenly applied to it. The polymer has very low viscosity, so that the coating is thin and even, but dense enough to protect the fiber. This coating layer usually consists of two parts. The primary coating is a very soft, elastic layer that dampens mechanical shocks and allows the fiber to bend. The secondary coating is harder and more rigid, protecting against external influences, dust, and scratches. These two layers are applied sequentially, one after the other, to provide reliable protection. After applying the liquid coating, the coated fiber passes through special forming rollers. They regulate the thickness and evenness of the layer, pressing the coating uniformly along the entire length of the fiber. These rollers are very precisely calibrated so that the layer is not too thick or thin. After the polymer has been applied and shaped, the fiber passes through a zone of ultraviolet light. Here, the polymer instantly hardens under the influence of ultraviolet lamps. This is a process called polymerization. Anyone who gets their nails done knows how this happens. Ultraviolet lamps emit light of a specific wavelength that activates chemical reactions in the polymer. Thanks to this, the coating quickly becomes solid, while retaining its elasticity and ability to protect the fiber. This is a very fast process. The coating solidifies in fractions of a second, literally. This method does not heat the fiber, so it doesn't damage it. This provides very strong and durable protection. The entire machine is equipped with sensors and control systems. They constantly measure the coating thickness, fiber feed speed, and uniformity of application. If the coating layer is too thin, or there are defects, the system either stops the process or adjusts the parameters to avoid defects. At the end of all this technological magic, a spooling module, rotating with a hum resembling the sound of a jet engine, only in miniature. The fiber, like transparent silk, lies down smoothly and precisely, coil after coil. It shimmers in the light of the lamps, reflecting cold blue and white hues. The spool moves smoothly, to the left, then to the right, with millimeter precision, as if an artist is painting pictures with movement. One wrong angle, and everything will go haywire, so the system automatically adjusts the rotation speed and fiber tension with surgical precision. Around are sensors, lasers, cameras. They carefully ensure that the fiber lies flat, doesn't twist, and doesn't create tension. With every minute, more and more layers appear on the spool. Imagine, in a few hours, there are already several feet of thin, almost invisible fiber there. And all this, without a single break, without a single scratch. Because even a micro crack, and the light signal will get messed up, like a radio wave in a storm. Before cable assembly begins, the fiber from the spool is carefully wound onto a production line. Since one cable usually contains several fibers, individual threads are combined into ribbons or modules. For ribbons, the fibers are arranged parallel in a single plane, for example, 12 pieces, and glued together with a special resin. This makes them easier to work with during connection. For bundles, the fibers are twisted into a spiral strand and placed in a plastic tube. These ribbons or bundles are then placed into buffer tubes, thin, flexible plastic channels that provide space for the fiber's slight movements. This is important because when the cable's temperature changes or it's bent, the fiber slightly expands or contracts, and the buffer tube helps prevent it from being damaged. A gel that repels water and absorbs vibrations can also be added inside these tubes. Around the buffer tubes, strengthening elements are added. Fiberglass or Kevlar, very strong threads that protect the cable from stretching. Metal wire, for additional mechanical strength or grounding. A central strength member, a rigid element in the center that maintains the cable's shape. These reinforcements are needed so the cable can withstand tension, impacts, bending, and remain intact for decades. All of this is wrapped in an outer jacket. This is a dense plastic or polyethylene pipe, resistant to ultraviolet light, moisture, rodents, and temperature fluctuations. The cable is tested. The bandwidth of each fiber is checked, as is its bending strength and resistance to moisture. Then it's wound onto large drums, marked, and technical documents are added, and it's ready for transportation and installation.